Okay, so today we will be starting with the part 1 of this XFLR5 how-to guide. You can call it as a hands-on tutorial. So this part 1 will be mostly based on the 2D airfoil analysis. So let's talk briefly about XFLR5. The official website is flashed on the screen. You can simply visit this website, and the latest version which I'll be using for these tutorials is version 6.47. So it's free of cost software. You can download this, and I would actually call this software as a wrapper just for Xfoil. So in the background, actually, this software is running Mark Drella's Xfoil code for airfoil analysis, which is a very important and very famous tool for doing airfoil analysis. And other than that, XFLR5 also consists of several 3D analysis methods in order to predict aerodynamic performance of planes and wings at low Reynolds number. And these methods are like vortex lattice methods, shortly called as VLM, and lifting line theory. And it is also offering stability analysis of planes. So the XFLR5 is, I would say, it can be divided into 3 parts. So the procedure will be as follows. The first step is always choose or design an airfoil. So if you have an existing airfoil available, if you wanted to do some design an airfoil, a new airfoil based on an existing airfoil, you have the luxury of doing this. And the second step is performing a 2D airfoil analysis. And this is a part 1 where our software is for this part 1, mostly we will be revolving around this section, which is performing the 2D airfoil analysis. And the third and the final section, or the part of this procedure, is the 3D wing and plane analysis. So let's move. We will first of all see how one can choose or design an airfoil in XFLR5. So let's start now with XFLR5. This is a simple basic window of this XFLR5 version 6.47 I'm using. So you simply go to File and you can choose Direct Foil Design, right? Or if you don't want to use directly go for menus, you can also opt for a shortcut key, which is Control+1. So XFLR5 also has the option of using a NACA foil database, as in the case of XFLR. So you can design 4 or 5 digit and NACA airfoils. So we will be starting with NACA asymmetric airfoil, very famous airfoil, NACA airfoil, which is 0012. And you can see this green one is kind of a spline foil or a baseline airfoil, but the one which we'll be using for our analysis is this NACA 0012. And it has a very simple graphical user interface. If you want to zoom in, you can zoom in, let's say, to the leading edge, and if you want to go back again, you could reset the view. Similarly, you could zoom out, and you could just by clicking the left mouse button, you can pan or drag the profile around, and it's simply just it's not really a 2D, not really a 3D kind of a view. It's simply 2-dimensional, so it's just a plain view. Okay, so mostly I would recommend it to use for kind of a general practice. I am using always approximately 150 points, which according to from my experience, which is more than enough to really get good results. Otherwise, in some cases where you have really highly cambered airfoils, not in this case, for example, you could also experiment by doing some more number of points and to see how it really works. But in general, kind of a very rough or a crude thumb rule, it works very well in most of the cases. So now we have changed the density, you can say a grid density of the airfoil or a point distribution. So XFLR asks you if you want to overwrite it or you want to have use a new name. If you want, you can also use a new name like refine, something else. But I will be happy. I just override this one. Okay. And XFLR also offers another option of using a DAT file, so a simple XY coordinate file, which one could also use. So for our 2D airfoil analysis study, another airfile which we will be using later on is a airfoil which is used mostly SG6040 in the wind turbine industry. It is used for the horizontal axis wind turbines for low-speed airfoils. So in order to really distinguish between two airfoils, one can actually change the colors. So we just change the color here, and you can see now the white one is the SG6040. We can see compared to the NACA0012, which is this one. Symmetric airfoil, and this is not a symmetric airfoil. It's really kind of a very, you can see it's a cambered airfoil, and it's kind of a real loading towards the trailing edge, the lower side, and it's much thicker compared to the symmetric NACA0012 airfoil. And as we did with the NACA0012 foil, we will again refine globally the number of panels or number of points, 150, and we're happy with it. So we need to just override the names. That's it. So I think it's quite straightforward, very simple. So we just end up our first part, designing an airfoil, as we have seen. So once you go through this stage or this step, just a small recap. Let's say you go to the file menu, and from direct file designer you could choose a shortcut Control+1 key, and we have already seen that it has an internal database for NACA airfoils. And if you wanted to use any other airfoils, you can have simply a DAT file, and then you simply import it in XFLR file. So the second step that will be performing 2D airfoil analysis. So once you have finished designing your airfoil, you will go to the file menu and start from Xfoil direct analysis. Or if you want to use a shortcut key, if you're an experienced user, if you have been using XFLR5 for quite a time, then you could use actually Control+F shortcut key, and then you will simply go into the Xfoil direct analysis. And then after you go into this mode, then you have to choose analysis and define an analysis for your airfoil, particular airfoil. So let's go back to the hands-on tutorial. So we will start, we go from file menu, we will go to the XFoil direct analysis. You can see we have two airfoils, NACA0012 and SG6040. Yeah, and we can actually, if you want, you can reset a foil scale. You can zoom in or zoom out by using your middle mouse button, your mouse button wheel. And XFLR, once you start your direct and airfoil analysis mode, it by default it opens all these 5 graphs. So we will now start doing the calculation for the analysis. Let's do first of all an analysis for NACA0012 airfoil, right? So we can simply say, okay, so these are the default options, I guess. Now it's looking quite good if we stick to automatic. So there are different types of options available. Well, we will be sticking just for type 1. So let's say for fixed speed, we will not use any Mach number because it's an incompressible flow. So we at the moment will be doing computations without a Mach number of about 0. And for this test case, we will use Reynolds number of 6 million. And As in Xfoil, XFLR5 is also offering the option of using transition. So if you, these are the default values. If you use a value of 1, this means that there is no transition, so it's fully turbulent you are calculating. If you wanted to use, if you have an experimental data available and you know the tripping location for your lower and the top part of your airfoil, you could actually specify this, but we'll be using no transition, so free transition. So we'll be happy with this server, and we wanted to use a Reynolds number of 6 million, and we will do a complete polar. I think this is happy. We'll be happy with this one. So you just start, even if you use that for a particular angle of attack, you could do a computation for a specific angle of attack, but we'll be interested in doing a complete polar, and we'll see later on that how the results matches with the experimental data which is available for this test case too. So let's do an analysis. And we can see it's saying that some points are unconverged because sometimes it reaches the number of maximum number of iterations limit, and this is kind of a common, I would say, a problem. As from the experience, it's the same as sometimes it is observed also in case of Xfoil. So, but overall, we are getting quite a good result. So this is the polars. You could see alpha versus your lift coefficient, your CL and the transition location on the top surface, and alpha over the CL over CD ratio, lift to drag ratio, your momentum coefficient. We can also compare that in terms of the pressure distribution. If we go at higher angles of attack, for example, at 10 degrees or so, this is the pressure distribution. You can see the suction peak is still increasing. Yeah, so if we keep on going to 20 or so, it's still also increasing. So, but this could also be the case, but in reality, it is not the case because the viscous effects are not actually calculated here. Okay, so I would say we just stop here, and then we will see how the results compare with the test case. So as I mentioned, we'll be using comparison with an experiment and XFLR5. So we use our first airfoil, which is NACA0012. And I'll be doing a comparison for in terms of lift coefficient and drag polar and some CP distribution at several angles of attack. For this experimental data is available. If you are interested, you can also download experimental data from here. Anyways, I'll be also writing this link in the description. You can also get it from there. So let's move. So this is an airfoil, it's a symmetric airfoil, and if we now compare, so the one with the orange color is XFLR5 prediction. We can see it starts from -5 towards 20. So because we are not even using a viscous calculation, so because of the viscosity, which plays a very important role at higher angles of attack, it gets really non-linear. So we can see it's kind of all of a leading edge type stall. It's an abrupt drop in the lift. So, but over and all in the linear region till the maximum lift coefficient, so which is about approximately, you could say 16-17 degrees or so alpha, compared to the experiments from Abbott and Wondorf and Lutzen, XFLR is performing quite well. Similarly, if we see also the drag polar, it's working very well till the maximum lift, and then in experiment we can see that the drag increases because of the viscous effect, and it's the stalling phenomena starts. But XFLR is using this inviscid theory. So let's do some comparison. So we have an experimental data available from Lutzen and Gregory. You can see also, if you are interested, you can also get these pressure distributions from the links mentioned before. XFLR is predicting quite well compared to the experiments at 0 degree angle of attack. So the pressure distribution is looking really nice. Similarly, it's the case at higher angles of attack, which is 10 degree. So if we can see it's probably 10 degree, it's matching quite well, and it's the same here. In terms of experiment, XFLR is really predicting the pressure coefficient very nicely. Same is the case at further higher angle of attack, which is 15 degree. So the results are looking quite good. Now we will move on to our second airfoil, which is in this SG6040. Is already mentioned. It's a low-speed airfoil. It's another classical validation test case, which is used quite famous in the horizontal axis wind turbine industry. It's used for low-speed wind turbines. So the airfoil is not really symmetric, yeah. And so let's do some airfoil analysis for this airfoil too. So the step will be, we will first of all choose the airfoil, particular airfoil which we wanted to perform the analysis for. So we just go again to analysis, define an analysis. So in the experiment they use actually two different Reynolds numbers, so 0.3 million and 0.4 million. We will be, for this tutorial we will be just using 0.3 million, and the rest of the stuff we will be happy with. It's all default, we're not changing anything. So we just start let's say from -10 to 15, something like this. I think this is, if I'm not wrong, the range of analysis is okay. So now we'll just start the polar and we will see how the complete simulation looks like. So it's finished, and if we go now to the graphs, another interesting thing, you could actually see that compared to the NACA0012, it's also a very good comparison because it's a symmetric airfoil, you know. And if we really see this blue one, symmetric airfoil means that you have a zero lift at zero angle of attack. So if we really zoom in at this graph number 2, by the way, it's another very good option in XFLR. So the graph numbering start from the top left, 1, 2, 3, 4, and 5. So if you just press from the keyboard 1, you will get the first graph. And if I press number 2, and I will get a graph, some alpha versus lift coefficient. Now we can see very well that the NACA0012 airfoil, it is getting a higher lift. But compared to a highly cambered airfoil, which is an not symmetric airfoil, so it's getting a zero lift at an angle of attack of, I would say, approximately around -4 or something like this. And because of having a higher camber, this airfoil is getting higher lift. So there is an increase in or shift with some specific delta from 0 to, let's say, about 0.4 or so at 0 degree angle of attack. Yeah, so you can actually fly with this much with higher lift, but it will stall maybe earlier. So this is another important effect we have seen just here. This is how the lift polar is looking like, and also drag. I would also like to mention, actually, if you want to change the graph or some parameters, if you know, let's say we wanted to see alpha versus CL, or alpha versus CL versus CD, so we can just, in order to see the laminar bucket, so we can just say, okay, x-axis is CD, you can choose CL here. So now you can see this laminar bucket. So this is kind of a laminar region, and you just on the graph which you want to change the parameters, so you just double click with your left mouse button, and then you will see this menu, and now you can choose which parameters you want to compare with what. So, and you can also export the graphs, which I actually did. I always do this, and then you can export it in Excel. So you simply say export graph, and then you name, and then you will be getting this CSV files, comma separated version. So it's values. It's a very common format for data exchange. So let's see now how it really resembles with experiments. We can see that once again the blue one is experiment, and the one with the orange is the XFLR5. So for this case, actually it's really predicting very, very well. So the lift coefficient is almost overlapping with experimental results. And similarly is the case also for the drag polar, and the results are actually very good. So it's again kind of an encouraging feature and encouragement for the students, and even for hobby plane makers, and also for other like model planes. If you're building like RC planes, remote control planes or so, it's very handy tool to see the performance, aerodynamic performance of your planes or wings. Yeah, and you can also, it is very powerful in designing airfoils. And similarly, we have just seen in terms of the graphs, you can import, export new different airfoils you have, and you can also export these results and compare with your other analysis. And similarly, in terms of the pressure distribution, if we wanted to compare this pressure distribution, for example, with some other airfoils, you just go there and you can simply export the graph, right? So I think that is almost it. That's it for this part one, which is I think kind of a first step for our series of several parts of this XFLR5 hands-on tutorial series. So I would say and encourage you to also support my channel, and if you really feel that there are some deficiencies, and then please feel free to write your comments in the comment section, and stay tuned for the part 2. So I'll be then performing the 3D analysis part, which will be this here, part of this XFLR5 procedure. So we will be actually using the 2D airfoil analysis, and we will simply extend it. So with this, I come to the end of this part.
So that's it from now. Don't forget to like the video and subscribe my channel. Stay tuned for new incoming videos. Thank you.